Hi everybody. So this next section has to do, or this last section of chapter 10 that we're going to cover has to do with, again, kind of putting everything together from the previous sections and determining which method to use. So again, there's kind of a flow chart you can follow like we've done in the previous sections. So basically, what's the parameter that's you're talking about? If it's a proportion, then you want to use this as your um, the normal distribution to determine your z-score. If it's the mean, right, provided that the sample size is greater than 30, or the data comes from a population that is normally distributed, right, use student's t-distribution with this test statistic. And this would be from 10.2, this would be from 10.3. Remember, 10.1 was just kind of an introductory section on hypothesis testing. We weren't really doing anything yet in terms of computations in that section. And then if you're testing the standard deviation or the variance, right, again, provided that the data comes from a normally distributed set, which again, in a lot of cases you can assume that, or there will be information given to you that says you can sort of assume that it's normal, right? Because if you can't do the test. You'd have to use a non-parametric test from like maybe chapter 15. Then again, you'd use the chi-squared distribution. Again, that's in 10.4. So just to remind you, there are, they kind of walk you through those things, right? Like on the bottom of page 509 and 510, it kind of walks you through the 4 steps or 5 steps to do that. And remember, in all these cases, you're basically, whether you're using the p-value approach or the the classical approach, right? You basically calculate the statistic, and then the classical approach, you compare that statistic to a statistic you would look up in a table or get using StatCrunch, and then again, so what you're doing is you're comparing the z-scores or the t-scores or the chi-squared statistics, whereas right, which correspond to an area, or again with the p-value approach, you're actually comparing the direct areas underneath the curves, not the number of standard deviations or whatever you are away from the mean. So again, you're really doing the same thing in the classical and the p-value approach, right? It's just one, you're comparing the scores which correspond to the area, and the p-value approach, you're comparing the areas directly, right? Okay, so that pretty much wraps up that section. I thought maybe although we're not covering 10.6 here, I thought maybe I'd just talk about this a little bit in terms of what this is about. Again, there isn't really any homework on this or anything, but I thought I'd just talk about it again because 10.5 is sort of a short section here. So this is about the probability of a type 1 error, right? So we talked about the difference between type 1 and type 2 errors earlier. And so we want to determine the probability of making a type 2 error, and then we want to compute something called the power of the test. So let's look at each one of these. So the probability of a type 1, to determine the probability of a type 1 error, first of all, what you want to do is determine the sample mean that separates the rejected region from the non-rejected region. And this procedure is listed on page 518 also. And then again, if it's a left-tailed test or a right-tailed test or two-tailed test, this statistic is roughly the same. And this should be p hat here. And then find the area under the normal curve to the right of the sample proportion found in step 1, assuming the particular value of the hypothesis, right? Or, if it's right-tailed test or two-tailed test, you'd do something similar. Again, this should be, I don't know why these umlauts or diaresis are here. These should be p hat u and p hat l. So let's look at an example here. So we tested the hypothesis that the mean trade volume of Apple stocks was greater than 35.14. So this would be our null alternative hypothesis. Sample size was 40. Level of significance was 1.3. Standard deviation was 15.07 million. Compute the probability of a type 2 error given that the population mean is 40.62. So again, throwing that into all that information into the test statistic, right? The mean here is 38.19. So for any sample mean less than 38.19, we do not reject the null hypothesis. So again, in this region, we would not reject the null hypothesis, and then we would reject H0 if it's greater than 38.19, which is where our score is here. So again, remember, this is the score, not the area. So step 2 then, this would be step 2. So compare these things, and then this would be the type 2 error probability region here. So the probability of a type 2 error, in other words, the probability of not rejecting the null hypothesis when the alternative hypothesis is true, remember that's what it means to be a type 2 error, is the probability that the mean is less than 38.19 given that the, sample mean, given that the population mean is equal to 40.62. So if you calculate that out, right, we're calculating a z-score, which will give you about 15.39%, right? So the probability of a type error in this case is about 15.39%, not terribly high. Now, as far as computing what's known as the power of the test, so the probability of rejecting the null hypothesis when the alternative hypothesis is true is given by 1 minus beta, and the value of 1 minus beta, or 100% minus beta, is referred to as the power of the test. The higher the power of the test, the more likely the test will reject the null hypothesis when the alternative hypothesis is true. So the thing that we just calculated in the last example is beta, so it's just 1 minus beta. So in other words, there's an 84.6% chance of rejecting the null hypothesis when the true population mean is 40.62. Okay, so again, I'm not going to really test you on 6.2. I didn't assign any homework for that except for maybe optional extra credit. So, but I just thought I'd go over that anyway, just so you can kind of see what that's about. So, all right, if you guys have questions about that or anything, just let me know.